second year PhD student at Northwestern, working with Shawan, and she works on secure multi-party authentication and other aspects of another problems in applied cryptography. And
okay. Thank you for hosting me, and today I'll be presenting this recent work, Scalable Mixed Mode MPC, which is a joint work with Kang Yang, John and Shao. Okay, this is not working. Yeah, so briefly I'll explain what MPC is. So essentially what happens is there are multiple parties, and each of the party has some private input X on which they want to compute a joint function. This function is public and they want to obtain this common output Y. They don't want any other party to know anything about their input. For example, P1 doesn't want P2 to know anything about X1 or anything else. So a simple example could be, how much do we earn? Let's say there are 4 people, they want to know the sum of all of their salaries. So typically what we'll end up doing is, we'll find a common friend, trusted entity basically, whom all of these parties P1 to P4 will send their salaries. The trusted entity will just sum up these salaries and send it to all the parties. But in real life we don't have such trusted entities. So what do we do now? So a simple thing could be that party 1 just samples a randomness, adds this randomness to its salary and sends it to the next party. The next party will now add its own salary to this message that it receives and do the protocol so on, that it sends to P3, P3 sends to P4 and so on. So eventually the first party receives the sum of all the salaries plus the randomness that it already has. So it will just reduce this randomness and send it to all the other parties. Basically here we have this assumption that only one of the parties will be corrupt and will try to know more than it needs to. So since P1 has this randomness, it will never, nobody will ever get to know more than the sum of their salaries. Yeah. So in this paper what we are doing is, we are dealing with semi-honest security and n-1 corruptions. So typically in this security setting there are 2 representations which are used. One is arithmetic representation, wherein each party actually has this share of X, which and these shares sum up to generate the original value. And there is the next representation is Boolean representation, wherein each party has a share of X and all of these shares XOR to generate the actual value X. Yeah, and both of these representations have their own benefits. Like in arithmetic representation, it is faster to do this addition or even multiplication of a 32-bit number or 64-bit number. And then there are Boolean representations, wherein you can easily do bitwise operations. Like when you need to do comparison, it is faster in Boolean than in arithmetic. So what we want to do is, we want to get the best of both worlds. That is, we want a circuit to have both the representations in it, which requires the introduction of conversion protocols from arithmetic to Boolean and Boolean to arithmetic. So when you are in arithmetic representation, you can use different computation methods like GMW or arithmetic garbling and things like that. When you are in Boolean representation, you can use GMW or garbled circuits. And then we want to be able to convert between both the representations. Like a simple motivation could be biometric matching. Let's say there are 2 entities, both have some data and want to do biometric matching on their shared data. So how will they do it? Biometric matching has these 2 parts. One is you compute the distance and then you want to find which is the closest, which requires you to do a comparison. So this distance computing is faster in arithmetic, while this comparison is faster in Boolean. So there we need to do this conversion, and there are many such other examples. So yeah, so in this talk I will just go through this preliminary, which is called homomorphic encryption, which we use throughout the paper, and then we design a lookup table protocol, which is a primitive and the core of our paper, which we use in all the conversion protocols and also the other results like we have on garbled circuits. So what is homomorphic encryption? So essentially homomorphic encryption is this magical thing which allows you to compute a function on the ciphertext. For example, let's say you had these encryptions of x and encryption of y, and you wanted to compute some function on x and y. So once you have this homomorphic encryption, you can do some kind of computations on these ciphertexts without decrypting, and you will obtain the encryption of the function if it was computed on the plain text. So there are different kinds of homomorphic encryption. One is additively homomorphic, wherein this function can only be linear, that is, you can only do additions. Then there are multiplicative homomorphic encryption schemes, wherein you can do multiplications but not additions. And then there are somewhat homomorphic encryption schemes, where you can do a limited number of both the operations, additions and multiplications. And then we also have fully homomorphic encryption schemes, where you can do any number of additions and multiplications, but these are typically not very efficient. So we most of the works use somewhat homomorphic encryption schemes to design efficient MPC models or outsource computation and things like that. So in this work, since we are dealing with a multi-party setting, we use this notion called threshold homomorphic encryption, where each party has a share of the secret key, additive shares of the secret key, and they have this joint public key. So since we have a joint public key, anybody can encrypt for the eventual secret key which is actually shared, and the decryption requires at least T parties, which is the threshold, to be online. Why at least T parties? Because the secret key is shared, so nobody can decrypt on their own. So in our case, since we are allowing for n-1 corruptions, you need all the parties to be online to be able to decrypt. Now why are we looking at homomorphic encryption? Because it doesn't seem related in any way to the arithmetic or Boolean representation that we saw. So we make a quick observation that it is easy to go from encrypted encryptions. Basically it is easy to go from a ciphertext to arithmetic shares when you are using certain LWE based and HE schemes. So what happens in these schemes is that the secret key is additively shared between all the parties, and the ciphertext and message have such a relation. So the goal here is that all of the parties have their own share of the secret key. They know this ciphertext C. They don't know what this message is. They just want to obtain the additive shares of this message. So what will we do? Each party will, so we have these three parties, right? So P1 and P2 will sample this random share for themselves, which is X. Here you can see that it is SK times C1, right? So you can imagine that what the decryption looks like is that P1 does SK1 times C1, P2 does SK2 times C1, P3 does SK3 times C1, and then all of them sum it up with C0 to obtain this message M. So the decryption share for P1 looks like this: SK1 times C1 plus this is just an error term which is like the noise for LWE schemes, and it subtracts this term. And it subtracts this X1. Similarly, P2 also does this, computes this decryption share for itself and subtracts this X2, and both of the parties send their share to P3. So now this party 3 can just compute SK3 times C1 plus C0, which is known by everybody, and then sum this H1 and H2 that it receives from all the other parties. So now we know that encryption to arithmetic share actually only requires each party to send one ring element to the final party, and that's how encryption to arithmetic shares is very easy. So now we'll just use this E to A and the underlying HE scheme to design this lookup table protocol. Okay, so the table here, basically for lookup table protocol, why we think the need for this protocol is that each function you can think of it as a truth table, right? And in the MPC realm, each party has a share of the input. So we can think of it like you have this public truth table and we want to look up at an index which is actually private. So our goal here is just to do a random cyclic rotation of the table and then look up at a public index which is actually generated by the private index and the random rotation that we do here. So how does it work? Basically each party, let's say we have this P1 will encrypt all the entries of this table, sample this randomness R1 and compute this mapping. Basically it will shuffle according to this mapping I XOR R which actually goes to I. So let's say this P0 and this was entry, this R1 was 1, so we want P0 to come at this position and P1 to come at some other position according to this mapping here. So P1 will rotate and then send it to the next party. So now P2 will also shuffle, sample its own randomness, shuffle the entries according to this mapping, re-randomize the entries. Why do we need this re-randomization? Let's say P1 and P3 were colluding. We don't want them to know this randomness R2 which was actually sampled by the second party. So we re-randomize these entries and send this final ciphertext to party 3. And here we needed to communicate only one element with the next party. And now that we have this ciphertext of the final rotation, Pn can just send the ciphertext to all the parties, and as we saw the previous sub protocol which was like encryption to arithmetic shares, all the parties just use that encryption to arithmetic share protocol to get these additive shares of the rotated table. Okay, so essentially what was happening was each party was just communicating with the next party for most part of the protocol instead of communicating with n-1 party, which is what is going to help in making the conversions efficient eventually. And now we'll just keep using this lookup table protocol throughout the talk. So if there are any questions.
So what's the final goal of this protocol?
So yes, so the final goal is to basically you want to look up at some index x which is distributed among all the parties, and this table for now we can just say that it is public, and you want to look up at this private index which was secret shared among all the parties. So now that they have this shares of this rotated table, they can just basically make this XOR R public because R was random, and then look up at this index XOR R. So essentially we wanted to look up in that truth table at some private index, but now we have this random rotation, so we have this public index where we want to look up in that table. Right. To make this public, you can just it's just 1 bit communication, right?
Yeah.
Essentially, or the log m bits, basically the size of the table depends.
Yeah. I'm saying like that. You said you wanted to keep people just talking to their neighbors, but for that part you will have everyone.
Yeah. But this is like for most part of the protocol, because what happens in the two-party setting is we need a point-to-point OT. So basically each party will end up having to do oblivious transfers with n-1 party, which turns out to be very expensive.
Yeah, it's keeping the table encrypted so that.
Yeah, exactly. Okay, so now we'll look at how we can do Boolean to arithmetic conversions using this lookup table protocol that we just saw. So the goal is that we have these Boolean shares of x, and we want to get the arithmetic shares of x. So I have this one here, but it should have been I. But yeah, so each party has these Boolean shares and wants to obtain these additive shares of x. So now if we look at x as an L bit number, then for each bit we can say that if we have this table which has entries 0 and 1, essentially what we want to do is just look up at index y to get y again, right? And in the previous protocol here, we had Boolean index but arithmetic output, right? So essentially that's what we have here. We have x as a Boolean share and we want to obtain arithmetic share. So for each bit we can just look up in this table using the previous protocol at this Boolean secret shared index and obtain the arithmetic share of the output, right? So once you have the arithmetic shares of each bit, all of them can just locally compute the addition, like 2 to the power of each index, and then obtain the arithmetic share of x eventually. But the problem is that each lookup required us to share m. If the size was m, we were required to share m ciphertext, right? And each ciphertext is extremely large. So what can we do here? So we end up using packing. Packing is something which allows us to pack multiple elements in just one ciphertext. So essentially you don't have to think of this notation as very complicated. It's just that each ciphertext is essentially a polynomial which has n irreducible roots here. And because of this notation, we'll say that these n irreducible roots are actually the roots of unity, but that doesn't really matter for your understanding. So basically each ciphertext has n irreducible roots. So essentially there are n coefficients, and in each coefficient you can pack one element, and this n is typically very large, maybe 8,000 or even larger than that. So yeah. But now previously you could see that the rotation was very easy because you had these two ciphertexts and you was just like shuffling it on your own, right? But now how do we do this shuffling or rotation, as we said? So I will just show a quick intuition, but that's not the actual protocol or all the details because it depends on the encryption scheme we are using. But I'll just show how it happens in these kind of, how the rotation happens in these kind of rings. So the operation is actually called automorphisms, and if the polynomial looked like this, which has n plus 1 coefficients here, so each coefficient is actually one element for us, okay? And these automorphisms are just some operation. Let's say this f of x has one root alpha, and then you apply this automorphism operation sigma on it. It will essentially move this alpha to sigma of alpha. So what is happening is we are just permuting the roots, or we can say that we are just permuting the position of the coefficients, right? Okay. So now we know how we can cyclically move these coefficients. However, once we have these packings, now it's no longer a cyclic rotation even for a size 2 table. Why? Because let's say you had this 0 1 0 1, okay? You don't really want to have like the second rotation value affecting the rotation of the first table, right? So what we end up doing is we end up doing a combination of some automorphism, linear combination of some automorphism, which is like a generic permutation, how you will do a generic permutation using these packing schemes. So I'll just go through this small example, but it can be generalized to any size tables and any packing size basically. So let's say P1 has packed these two tables 0 1 0 1 and sampled two random rotation values. Now it will rotate the first table according to this R1 of 0 and the second table according to R1 of 1, and then encrypt the packed table, okay, and send it to the next party. So after receiving this table, P2 will sample its own randomness, basically by which it wants to rotate the first table and the second table. So I'll just show you a quick example. Let's say this x was 0, that is we did not want to rotate these two entries, okay? So you want A and B to be as is in the product. So you just multiply it by 1, right? And then you don't want anything to come from here, so it's just 0, 0, 0, 0. So you will have AB at the end from here. And now if x was 0, that is you want, x was 1, you wanted to move this B up and A down. So it's just you have this 0, 0 here and 1 from B, so it gives you B here, and then 1 from A in the next rotation. So this is just one rotation up, one rotation down, because remember we are only able to do cyclic rotations from this automorphism thing. So we have to do this 2 cyclic rotations and then this linear combination on the pad.
Okay, so what's the form of the table now?
So now the table is packed as a polynomial. Okay, so we can't really shuffle the elements as we want, because now it's in a polynomial and you can't move the entries as is. So what happened was, this automorphism, it allows us to do a cyclic rotation. That is, you can move you can't just shuffle randomly, but you can move A0 here and AN to the next, right? So that's what these automorphisms allow, and you can have all kinds of automorphism. That is like, you can go from xn to x, xn to xn minus 1. All of these cyclic rotations are possible.
It's n+1.
Yeah. But you can't do a random shuffle here. So when we want to do this permutation eventually, we need to do a linear combination of multiple automorphisms. So okay, so here what we are doing is, this is nothing, it is as is. Okay, and here we just move the entries 1 up, like B, C, D, A. Now before it was A, B, C, D. And here we are moving -1 rotation, basically D, A, B, C. Okay, so since we only have a size 2 table, these automorphisms are sufficient. But if you have a larger size table, you will need more. Yeah, so these are just 2 tables, right, of size 2, 0, 1, 0, 1. This can be generic, we can have many tables packed essentially. So for the implementation we were using, we had like 4,000 tables packed in just one ciphertext. But like for simplicity, I'm just showing that, okay, let's say you have 2 tables which are packed. How would you go about doing this shuffle of the 2 tables together? So basically we just do 1 rotation up, 1 rotation down, and then have this linear combination help us get the actual values that we wanted. For example, let's say x was 0, y was 1. Okay, so x is 0, so we want a, b to come as is in the eventual product, right? So we are multiplying here by 1, so a and b will come through. This c is already not contributing because we don't want it in the second value here. This d is not contributing. Now x is 0, so b will also not contribute. Now x is 0, so a will also not contribute. Now and y is 1. Okay, so we want d and c instead of c, d. So here we'll just multiply by 0, so this will not contribute. And then here we want this d to come through, so we are multiplying by y, which is 1. A will never contribute, we don't want this to contribute anytime. And then this b we don't want to contribute ever, so we'll just multiply with 0. And this c will multiply with y, because if y is 1, we want this c to come in the lower position. So essentially this is just a permutation that we are doing.
So what is the tilde?
Oh, the tilde is just not of x, not of y. Just, yeah. So if x was 0, we wanted 1 not of x, not of x. So 1.
You want to also be able to move a all the way down.
We don't really want a to come all the way down. That's why we'll just multiply with 0 here. We just want a and b to be in these first 2 positions always. C and D to be in the next 2 positions always.
How does it scale when you have
It scales very well because it doesn't really matter if you pack 2 or if you pack 1000. The polynomial has 8000 slots, so it is up to you if you want to use it to the maximum efficiency. Right. No, you'll always have three things if you just, so these size of the linear combination, it only depends on the size of the original table. For example, here we have 0, 1, so the size of the table is 2, right?
Just need as many pins as to
Right.
all the way through the first round.
Exactly. So it doesn't matter how many tables you are packing. What matters for this permutation is what is the size of the table. So in the paper we mostly only need this size 2 tables. So it works very well. We haven't tried with like larger tables like AES, S-box and things like that, but that could also be interesting, I guess.
There you would need ABC,
Yeah, because I honestly I don't think it would be very efficient, because this is like computationally a very heavy operation, but here we only need to do a very small number, so we are very efficient. Yeah, I guess then it will just come to like communication versus computation trade-off, then it will come to, yeah. Okay, I guess so. So it is clear, right, how we get this rotation here after we have packed. So now we know that for each bit the parties have this arithmetic share of each bit, right? And so to obtain this arithmetic share of the value x, they will just locally combine these arithmetic shares for each bit. This should probably be L minus 1 since we had a L bit number, but I guess it's understandable, right? And then for each conversion we only have this much communication. Essentially each ciphertext is packing n elements, so n by 2 since we have a size 2 table, and times L because the number was L bit. And to briefly tell you what it is actually, is that ciphertext by n is typically very small, maybe it will be 2 or 4, but not larger than that, at least in our implementation. So this turns out to be a very small amount of communication for each party. Okay, so now we'll look at how we go from arithmetic to Boolean. Okay, so for arithmetic conversions, what we have is these additive shares of x, and we want to get Boolean shares of the Boolean shares of x, right? So in the previous protocol, Boolean to arithmetic, what was the benefit is that the lookup table protocol allowed us to look up at a Boolean value and obtain the arithmetic value, right? But that is possible because we could go from ciphertext to arithmetic shares, but we don't really know how to go from ciphertext to Boolean shares efficiently. So we can't make use of the lookup table protocol directly, but we see that our Boolean to arithmetic protocol is highly efficient, so we just end up making use of that B2A protocol. So what we do is we sample these random Boolean shares RB, and then use this Boolean to arithmetic protocol to obtain these arithmetic shares of these randomness. So we generate these pairs of random Boolean and arithmetic shares, and then we reveal x minus r in the arithmetic setting. So x minus r, like it hides x because r is random and we only use this randomness once. So and then eventually they can just compute x minus r plus r because you have Boolean shares of r. So they can just compute this x minus r plus r in the Boolean circuit and obtain these Boolean shares of x. So this is independent of the input. So we do this in the pre-processing phase, and x minus r and x minus r plus r, we compute this in the online phase basically. So we divide this in two phases, like pre-processing and online phase. But the problem is that since we are using packing, these arithmetic shares are modulo prime. This is not modulo 2 to the L. So if we were not using packing, then it would have been fine, but since we are using packing, we have this arithmetic shares in modulo prime. So this randomness is actually not going to be uniform if you sample Boolean shares. So for example, you can say that you had a 32-bit number. If this was actually always in mod 2 to the 32, then you can just sample like 32 bits of randomness, and you always know that the XOR of this random value is also going to be in 2 to the 32. But now we don't really know if this R is going to be smaller than this prime P or greater than prime P, and now it's no longer uniform. So so now how can we make this R uniform here? I'll just say briefly that when you have like a larger number like 2 to the 64, it is not necessary to do anything on top of it because it is statistically secure. But when you have small numbers like 32-bit numbers or 16-bit numbers, you need to do something on top of it to make it uniform, because it doesn't provide enough statistical security. So a naive solution could be just have a comparison circuit here, and then we discard if it is greater than prime P, or if it is less than prime P, we just keep moving forward. So what we find is that because we are using these LWE based FHE schemes, we have special primes. So for 32-bit we had this prime 2 to the 32 minus 2 to the 30 plus 1, wherein the maximum possible R was this beautiful looking number 1 1 and then all the trailing zeros. And we saw that in the B2A protocol we are getting arithmetic shares for each bit, right? So essentially what we want to do is we can just compute the sum of the trailing bits and then have these two multiplications, right? You have the sum of this trailing bits and this and you multiply it with this bit and this bit. So we actually only have two multiplications because this addition is free when we are in arithmetic shares, and then we have these two multiplications. So now if this product is 0, then it is going to be less than or equal to this R. If this product is 1, then it was most certainly the greater than or equals to R, greater than R, not equals to, greater than R, right? So just giving two multiplications allows us to check if this R was greater than P or less than P, and then we can just move forward with the protocol as is. So this is just a way to do rejection sampling efficiently.
So this all done in some pre-processing?
Yeah, this we can do in the pre-processing phase. Okay. So so that was it for the protocols, and I'll just briefly show the results that here for B2A we wanted to. So all the previous protocols I have actually squared or cubic complexity, previous state of the arts, but you can see that our graphs are actually linear, and this is the execution time.
For some that number.
Right. So this is like amortized cost.
Okay.
Yeah. So about how many we need to pack, it actually ends up depending on the number of parties, because if you see the protocol, actually in the protocol each party needs to wait for the previous party, right? So so then the number of rounds actually is dependent on n. But if we do some engineering things like pipelining and stuff, you can still have it like linear complexity, otherwise it will be squared. If we don't do any kind of pipelining, this graph would be quadratic. But since we can do pipelining, it's linear. And because we need to do pipelining depending on the number of parties, actually this pre-processing we do, like the number of ciphertexts we do in one round is also dependent on the number of parties. Yeah.
It's a moderate number? Or?
Yeah, it's a moderate number. I think so. You can think of it as so when you have 64 parties, you will okay. So each ciphertext actually has like 4,000 or something. So 4,000 times 64, which is fine. Yeah.
So, and this is online time?
No, this is just pre-processing.
This is pre-processing.
Yeah, online is not so. Okay, so here in this graph it's actually both combined, but when we compare, we only compare the pre-processing, because the online phase is actually interchangeable with all the existing protocols. So here it is like the sum of online and offline, but when we do the comparison, it is actually just the pre-processing that we compare, because even though it's different, you can actually just plug in with different protocols if the other one is better in performance.
What's the WAN versus LAN?
Yeah. So the WAN versus LAN difference is actually not much. It's just the bandwidth difference that is contributing. Because the communication is very low. So for the previous protocols, the WAN versus LAN difference is larger than ours, because the communication there is much higher, because each party is communicating with n-1 parties all the time. Okay, but the A to B curve here is quadratic, because we ended up doing that circuit computation, which requires like communication with all the parties, right? So the B to A graph is actually linear.
Circuit computation is not using what?
GMW, yes. And here we have the comparison. So for communication, we find that this blue line is ours, and this red line is of MOTION, which is another state-of-the-art protocol, and other one is MP-SPDZ, which is very famous. So we find that our communication is actually much lower than both of these frameworks, and also that we are able to test up to 128 parties very easily, but both MOTION and MP-SPDZ we were not able to run because they require a very large number of resources. So the communication is very low, and what was surprising is that the performance starts getting better with 4 parties even, which we were not expecting. And even for like the execution time, ours is significantly better than both. MP-SPDZ is a bit lower for A to B, but for B to A, the computation time is actually very low in comparison to both the other protocols. And okay, I guess I have time, but there are more results in the paper on garbled circuits and end-to-end use cases. So you can have a look there. I'll just briefly go through what I'm working right now since I have time. So right now what I'm working on is MPC compilation. Basically in this work what we did was how to improve the efficiency, and now what we want to do is how we can improve this compilation part, because in MPC people are designing many new IRs which are specific to different backend implementations. Like they will design something which is specific for MP-SPDZ or specific for MOTION, and then what they end up doing is design a very specific language just usable for their particular intermediate representation. But what we are trying to do is how we can just use any language. Like in general purpose computing, what happens is there are 3 divisions in the compiler's phase, which is one is front end, that is these languages C, C++, and then it will go into one intermediate representation which will be hooked with any kind of architecture. So we want to achieve the same thing for MPC, and we also are trying to utilize the existing work which has been done in general purpose computing. Essentially we have these compilers for C like Clang, and you have compiler for Rust. All of these compilers compile these languages into a common IR which is called LLVM IR. So in this project what we are trying to do is how we can just use LLVM IR itself and hook up with these backends.
Front end you are expecting somebody to provide their functionality as a
No. In the front end, we don't want the user to we don't require the user to know anything about how to write oblivious programs or things like that. For example, let's say you wanted to compute this Dijkstra do Dijkstra, okay? So you just specify what is secret shared, and our compiler will end up making the program oblivious, choosing which protocol you want to use where.
how is the X plus algorithm, like you just write it as a...
You just write it normally, standard algorithm.
So that's actually the best case, like the functionality scope, like the trusted party scope.
Yeah. Just like you would write code for a trusted party, but you specify what is secret shared. So during the compilation, we know how to make this program oblivious. Yeah. So right now we'll just make the program oblivious and do some optimizations on it. So why we end up going with LLVM and not designing a new IR is, once you design a new IR, you need to write all these basic optimizations again. Like for general purpose computing, there are many things written like vectorization and other things, like you will remove the things which are not used, and basically dead code elimination and stuff like that. If you make a new IR, you have to write all of those optimizations again. But that's why we are trying to make use of LLVM. Yeah.
Yeah, this is probably about, so everything about software, we have
Yeah.
something about these compilation also.
Right.
But so here your approach is you want to make arbitrary program
Right.
and write it as...
Yeah, exactly.
And in our approach, we are looking at like the PC functionality itself, you write very carefully.
Yeah.
So there's no, so it would be handwritten.
Yeah.
So here, if we have, so you need to support things like all the features that are in the MPC.
Right.
So branching.
Right. So that's why we'll have to make the program oblivious after compile. So Clang will just compile it normally and the program will be non-oblivious, right? But then we'll do some optimization passes and make the program oblivious. And so once the program is oblivious, like you know which branching was on some private variable, right? So we can just change the control flow graph basically. And then there are some other intricacies, like for LLVM things, there are a lot of things which depend on the control flow itself. So we need to make sure that the eventual program is also correct. But yeah, those are all the intricacies, which is why it is a bit complicated. But the core idea is that we want to shift the onus from the user, that they don't have to know how to write oblivious programs. And even for researchers, we don't have to write all of these optimizations again, because it's just a tedious task to see what is done in general purpose computing and then write it again. Of course, you can always write special optimizations for MPC, like we want lesser number of non-linear operations and stuff like that, which is not really a requirement in general computing. But these things you always have to write, right? Yeah. And the other thing is just improving this OLE generation, because right now what we need is actually, we need communication which is linear in the number of relations we want. But there are some works which are using pseudo-random correlation generators for sublinear communication. So I'm just looking into that also.
So you want to implement those in PCT?
Yeah, maybe implement and also improve.
The implementations already exist?
No, the implementations don't exist. They are just like theory works which show that, okay, we have these estimates and it's probably better than the existing ones, but nobody has actually implemented it. I'm not sure why. Yeah, okay, that's it. And you can find the paper on it.